Yeah, so so this is you can go back on the slide. Yeah, this is now we can start from we last with this is our last one, this one.
That one.
The next one.
Which one? This one. We are now on this one.
Yeah, this one was the last one.
So we discussed this one.
Yes.
92. Okay, so we start from there.
We start from there.
Okay, thank you very much. So again, is it afternoon? Oh, it's already afternoon. Good afternoon, class. I hope you are ready to learn. I know Fridays are usually tiring days after the whole week, but let us be ready to get more of this information. So I've been advised that the last slide that we looked at, we already had started on the benzomorphans, and we discussed at length the difference between the morphinans and the benzomorphans. Of course, of much importance, where we did mention, is the fact that we have lost a whole ring C. And in losing a whole ring C, which was part of the bigger structure, in losing the whole ring C, the numbering must change. And it's very important for us to understand the numbering changes, so that now we start from, with 1 prime, 2 prime, 3 prime, 4 prime. So the numbering of the phenyl ring is actually not part of the numbering of the ring C and even ring B. We number the phenyl ring on its own using prime, and then we start on the previous position 9. We give it 1, and then we move, as we said, anti-clockwise number, so that the former position 13 carries position 5, and now we go around ring B. And that we discussed, and I did mention, and I'll still repeat it again, that any time you're answering a question, especially when it deals with structure-activity relationship, kindly, even if it's a general structure, lift it from the question paper, put it on your answer sheet, and number it appropriately, so that whichever position you mention, whatever is on your mind is what you will actually be telling me, and I will be able to understand it better. Of course, I understand it, but I need you to make me understand. So again, of course, we are reminding ourselves that position 5 and 9 are very important. If those positions represent the vestiges of ring C. And the orientation of those groups, as we mentioned, very important. Position 5 must always carry the alpha orientation. It will be cis to the benzene ring. And position number 9 can carry either the alpha or the beta orientation. And if that happens, if it carries the alpha orientation, the resultant compound is almost, but slightly more active than morphine, but almost equipotent, and therefore the toxicity will almost be equivalent to that of morphine. When it carries the beta orientation, you get the beta compound, then you find that the resultant compound has much more activity, and that compound, as we discussed, will have more. We did mention that it will have more toxicity, or it will be more liable to addiction. I think we were able, that is just reminding us, and I think we were able to mention that, and that stereochemistry is very important. We did mention that position, the previous position 3, which I believe now is 2 prime, can carry either a methoxy group or a hydroxy group. But with the number of the questions, the compounds that we're giving examples, pentazosine, phenazosine, cyclozazine, and metazosine, these ones, that position actually carries a hydroxy group. We also did discuss phenazosine and compared it to phenyl ethyl morphine. And we are saying because of that huge group, that compound has the ability to interact with the allosteric A site within the morphine receptor, or within the opioid receptor, to give us, or for it to act as a very, very potent agonist, as a very, very potent agonist. I think we were able to get to there. And I think we also did mention that these compounds, when you put a group that is responsible for antagonist we did mention it was, I think, much higher. I don't know whether we had got there. You're saying this is where we have gotten to, I hope. More, yes, yeah. So that we had discussed. So we move on to the next slide, and this is just showing us the various compounds. That is metazoxine. It is a prototype, and you can see every position from position 5 and position 9 and position number 2. All of them have the methyl group, and they have small alkyl groups, and that is a prototype in this group. And then we have phenazoxine, and that resembles phenyl ethyl morphine. And what we are saying is that this group is large, and because it is large, just as we explained with phenyl ethyl morphine, it is able to interact with the A receptor. And in interacting with the A receptor, the compound has very high agonist activity. Then we go to pentazoxine. When you look at pentazoxine again, we see that this compound group there is much larger than it is within. If you look at the carbon atom, is 1, 2, 3, 4, 5, with branching, with also unsaturation, and therefore it brings in both antagonist and agonist activity. But again, remember we said the ratio of agonist to antagonist activity is much, much higher. Also, when you look at ketozoxine, I hope we did mention, if you look at that structure, it's a little bit different. In that position number 8, we do have a noxo group, unlike any of the other compounds. And of course, at position number 2, again, we have the cyclopropyl methyl group bringing in antagonist activity, and therefore the compound will be mixed antagonist, agonist. And the same case applies to cyclazozine, but we did mention that that compound has a lot of hallucinogenic activity, and it is not used because of the fact that it has quite a lot of toxicity. But we note that again it has that compound or that group that is found in naltrexone. It introduces antagonist activity, but the compound will have both agonist and antagonist activity because we did mention that these compounds, when you look at the benzomorphans, they have higher agonist activity to antagonist activity. So we can note therefore metazosine is a prototype with higher lipid water partition coefficient than morphine. Cyclazozine, which has the methyl cyclopropyl group, is a potent mixed agonist antagonist. It has high lipid water partition coefficient or high lipid solubility, but high incidence of hallucinations, and therefore it is not a good compound for clinical use. Phenazoxine, again, a mu agonist, and this is just what we had mentioned before, is more potent than morphine due to it has a phenethyl group that interacts with the A site. I hope we had said the same when we were looking at phenethyl morphine, but I was also got to the receptor and we look at that. It has also very high lipid solubility. So not only does it have affinity for an A or allosteric receptor, which we call A receptor, it also has high lipid water. It has also high lipophilicity for the facts that we have mentioned. The benzomorphans do not have a hydroxyl group, or we have removed the hydroxyl group at position number 6. These compounds, and of course we have added the phenethyl group, much higher lipid solubility, giving us very good activity. Ketozoxine has high affinity for kappa receptors. And one thing we notice that although the liver compound has high receptor, even as an agonist for kappa receptors do not have as much analgesic activity like mu receptors. It is the mu receptors that give optimal analgesic activity. The kappa receptors do not. They are not as effective as the mu receptors. Pentazosine is a synthetic opioid that has also both partial agonist and antagonist activity, as we have mentioned, and you can say it has weak antagonist or partial agonist activity to the mu type opioid receptor with full agonist activity at the kappa receptor. But although it has full agonist activity, as I have said, it is not the kappa. The kappa receptor does not give maximum efficacy. It does not give as much analgesic activity as the mu receptor. The mu receptor is the one which is optimal for analgesic activity. So the minute that molecule has partial activity at the mu receptor, that compound cannot have, will have, as you have said, it has passive agonist, it has antagonist activity at the mu receptor, and that's why we are saying that compound, we have both antagonist and also antagonist, and both antagonist and also agonist activity. I don't know whether we had looked at the receptor, because if we hadn't, it is important that I thought I had the receptor somewhere. So because now after this, I'll go to the 4-phenyl piperidines. We are done with the benzomorphans. I'll move to the 4-phenyl piperidines. But before I go to the 4-phenyl piperidines, I would want us, sorry, I did not post the receptor earlier. Let me look, I'm looking for that receptor so that I can explain the huge group we are talking about. This is our receptor, so that we can understand what we are talking about. So when you look at the morphine receptor, this is, or the opioid rather, let's call it, that one is too big. When we look at, I think I explained this. Did we look at the opioid receptor class? So that I don't waste more time. Class, did we? Somebody, did we discuss this opioid receptor? Class,
Yes,
I think we did, yeah?
Yes, we discussed.
We did, yeah?
Yes.
Fine, then we don't need to go back, because I've just remembered. The problem is I have more than one class, I'm teaching the same stuff. So that's why I have to be very careful. So we discussed the opioid receptor, and I did explain at length that if you have a huge group, especially when it's an alkyl arene at both position 7 or position number 17, either of those two positions, all depending now on the compound, if the numbering will change, if it's a benzomorphan. If you have that compound at those positions and attached to nitrogen or attached to the appropriate carbon, but we do not have those compounds for the benzomorphans. We realized we have those compounds for the morphine analogs or the unylated compounds, and that huge group interact with the allosteric center or allosteric site. Once it interacts with the allosteric site, then there is more affinity. And once you have more affinity, there is a possibility of higher agonist activity. And that is why phenazosine, phenethyl morphine are very strong agonists. That is why when we talked about etofine, it has, although it is not a phenyl group, it still has a large group at that position, and it could approach that receptor and have some sort of interaction, of course, and the compound also has very, very high lipid solubility. So I think with that, I hope we can be able to now move on to the 4-phenyl piperidines. And if you see the name, 4-phenyl piperidine. So we have now left with a phenyl and a piperidine ring. And if you look at this compound now, this is our phenyl ring there, and that is our piperidine ring. So of importance now is to note that there is no more fusion. If you look at the benzomorphans and you look at all the others, benzomorphans, the morphinans, the 4,5 epoxymorphinans, all of them, the rings are fused to each other. But now when we move to the 4-phenyl piperidines, it's something we note. There is no fusion. These rings are joined through a single bond. So these rings are joined, as you can see, unfortunately, it's not clear. The rings, as you can see, that is our phenyl ring joined through a bond, a sigma bond. That's what we call a sigma bond, to the piperidine ring. And we have only 2 rings, which are, of course, not fused. And once rings are not fused also, the rigidity, the molecule, usually becomes more flexible. The molecule is a little bit more flexible when you do not have fusion. So you can have the general structure. So when you look at this now, you can have this as a general structure where you have that ring there and you have that other ring there. You have R1 at position number 1. Again, if you look at this compound, it is important to note that the numbering again changes because we have also changed. Even now we have removed B completely, the former B, and we are only left with ring A and ring D. So we have 2 rings. So again, the numbering changes. We start where the basic numbering now goes the piperidine ring. The former position 2 of the benzomorphans becomes position 1 of the phenyl piperidines. So the nitrogen carries position 1, and then position 2. This was our former position 15, position 16. So position 16, sorry, position 15. So we have position 1, 2, 3. This was our former position 15, position 13. And you can see it still has a substituent. If this substituent has a carbon, it means our position 13, it is still a quaternary carbon, something we require for the morphine rule. So you can see at that position number 4, you have that substituent R2, and that is a position 5 in the benzomorphines. Then you have position 5, and then you have position 6. So here you are numbering each ring nowhere you are saying looking at intersection and moving this way. First of all, you number the phenyl ring going clockwise, starting with the point where the substituent, where the bond joining the phenyl ring. So you number 1 prime from where the bond, which is joining the phenyl ring to the piperidine ring, is originating from, and you go clockwise 2 prime, 3 prime, 4 prime, 5 prime, 6 prime. So you can see again here in the phenyl piperidines, we are looking at the 3 prime. The 3 prime now is a position which is supposed to be similar to the 2 prime of the benzo, similar to the 3 position of the morphinans and the morphine analogs. So here it is 3 prime. And that's why, and you see that position here, we are still retaining that position. Yes, we have done it in all the groups. And again, of course, if you have a hydroxyl group there, we would expect that compound to be able to interact with the area that the hydroxyl group in morphine interacts with. So that position is very important. That position here, which allows this carbon here to be a chiral center. Remember, the quaternary carbon, according to the morphine rule, is directly attached to the phenyl ring. That does not always happen, but for maximum and good activity, if that happens, then it gives you good activity. Then again, look at the nitrogen in the piperidine ring. The nitrogen is still tertiary, and it still has a group, just as we have discussed in the other compounds. Of course, we do not have the ring B, we do not have the ring C, so we cannot talk about C being saturated or not saturated, those two rings. So that is one way you can draw the general structure of the phenyl piperidines. You can also draw the general structure of the phenyl piperidine in this very simplified manner, where you just draw your piperidine ring. And of course, when you draw your piperidine ring, remember this nitrogen carries position number 1. It doesn't matter whether you go clockwise or you go anti-clockwise, the numbering will be the same. So position 1, you have that position 2, that is position 3, position 4, position 5, position 6. And no wonder we are calling them 4 phenyl piperidines, because at position number 4 of the piperidine ring, that is why we are getting the phenyl ring. So we are therefore saying one of these substituents, R2 or R3, must contain a phenyl ring. So one of these substituents, whether R2 or R3, one of them carries the phenyl ring. As to whether it is substituted with the hydroxyl group or not, that's a different story. But kindly note, in the phenyl piperidines, you can also have position 3 having a substituent, and that is what we are calling R4. So that is very important for us to note. In most of the compounds, R4 is a hydrogen, but there are some compounds that you see where R4 is a small methyl group. And when it comes there, kindly note, if that is a small methyl group, that position now there becomes a chiral center, and therefore the stereochemistry of that ring there. Hello. Good afternoon. Yeah. I think so. Wacha kidogo. When do you want to bring them? Although at the moment I'm in class, eh? So I'll be in class from 2 to 4. I'm not, just give me a minute, I'm talking to the class rep. Hello, Lennox. At the moment, I'm in class, and I'll be in class between 2 and 4. So, Lorenz, if you are willing to bring them after 4, you bring them tomorrow. After, you will drop them at 4. Okay, fine. Not 4, because now I have to organize with the border to come and pick them. So perhaps you get there by 4:30. No problem. Oh, that's hour. You can alert me when you leave. Thank you. Sorry about that. It's the class of the 5th years. They want to print the assignment. So we were therefore saying that we note that is position 1. And this nitrogen, just as we have discussed with the other compounds, it can have different substituents. It can have a methyl group, it can have larger substituents, and the influence most probably will just be the same as we have already discussed. As I was saying, the only major difference is position number 3 of the piperidine rings, that in the 4-phenyl piperidines, in some of the compounds, you have a substituent at position number 3. And once you have that substituent, position number 3 automatically becomes a chiral center. And it was found, since these compounds have a lot of stereo selectivity, even the stereochemistry of that position number 3 influences activity. So I hope we are together. The reason why we have an R4 there is that within the 4-phenyl piperidines, you can put a small group at position number 3 of the piperidine ring, and once you put a small group, it has an influence on the stereochemistry. So there is one isomer which will be more active than the other isomer, and therefore that makes a difference. Of course, if when that becomes a chiral center, kindly note that also is a chiral center. That is also a chiral center. And when that is a chiral center, and that is a chiral center, it means you can get 4 enantiomers. And out of the 4, it is 2 of them have activity, although 1 will have more activity than the other. So that group there, again, complicates just a little bit the chemistry of the 4-phenyl piperidines. So when we look at this is the very, very general structure, whereby we are saying, as I have said, I repeat again, either of this, one of them, must be a phenyl group. One of them must be a phenyl group for the 4-phenyl piperidines. And then the other will be, we will see, it can differ. It can be an ester, it can be a different compound with retention of activity. As like you can see an example, which I have drawn here. Here is our 4-phenyl, that is our piperidine. That is carrying position 1, position 2, position 3, and you can see our position 4. Here is our phenyl group. But you can see also at that position 4, we have an ester. At that position 4, we have an ester. When we have an ester has a carbon there. So this position 4 is still a quaternary carbon. So therefore, we are saying at this R here, there's one of these groups here. We say R2 is the one which is a phenyl group. R3 can be different groups. Sometimes we find it's an ester, it can be a ketone, and any other group that we will discuss. So I hope you're together up to there. So now let us look at the examples. I want to reduce this. Happened a bit. Anyway, I think we can still see it the way it is. All right. So we are looking at the examples of compounds that include the 4-phenyl piperidines. And the first compound is a compound we call meperidine or pethidine. Meperidine, kindly note meperidine or pethidine. Pethidine is a very important drug. When you go for your attachment, and for those who will have an opportunity of going to labor ward, they will find pethidine there, because pethidine has lower activity, lower analgesic activity than morphine. So out of the analogs now, you can see we started with the morphinans, they had higher activity, the benzomorphans had higher activity, but when we go to the 4-phenylpiperidines, the actual 4-phenylpiperidines, we find that the activity is much lower than that of morphine. So you find meperidine or pethidine has much lower analgesic activity, much lower toxicity than morphine. So you find pethidine for those women in very painful labor, sometimes very, very painful, you find that they can be given pethidine or meperidine, and because it doesn't have a lot of harm to the fetus. Of course, the fetus might be a bit drowsy, but when given, of course, in the therapeutic doses, it's very important, and it will relieve the labor pains. Or that is you only give it when you find that the lady or the mother cannot tolerate the pain. There is some extreme pain that a person cannot tolerate, and it's like that pain can send somebody to become almost crazy. So when you inject them, you calm them down. It's also an analgesic, and therefore relieves the pain. So again, please look for that drug when you go for your attachment in labor ward. So when you look at that drug, it has R1 as a methyl group. This is our R1, very small methyl group, similar to morphine. When you look at R2, a bit like morphine, it is a phenyl group. I hope you can see that. When you look at R3 is an ester. R3 is this one, is an ester there. But R4 is a hydrogen. So that is the structure of meperidine. I hope you are together. Then we go to the structure of bemidone. The compounds that we call bemidones are compounds where the phenyl ring that we bring in, we have said we bring in a phenyl ring, it's joined there. So that is ortho, that is meta, or the position we call position 3'. Remember us saying position 3' can have a hydroxyl group. In meperidine, you can see position 3' does not have a group, because you can see this is only a phenyl group. But we did mention that we can introduce, just like all the other morphine analogs, we can have a hydroxyl group now at position number 3. When you introduce a hydroxyl group at position number 3, the resultant compounds are called bemidones. So bemidones is where the phenyl ring has been substituted at the meta position. You can still see we have an ester. At that position, R4 is still a hydrogen. Then we have properidone. Again, properidone, the only difference is the group that we have. Everything else is the same. I want us to note keto-bemidone. So you can see the bemidone. We've already talked about bemidone. So we expect that when we talk about keto-bemidone, we have the bemidone, and you can see the phenyl ring already has a hydroxyl group, making it a bemidone. Then you can see it's a keto, which means in place of the ester that we have in meperidine or in bemidone, there is a keto group. And indeed, look at this. This is a keto, so that group is like that. And then C2, CH2, CH3. Whereas when you talk about this one, it's an ester, so it will be C, double bond O, and then there is an oxygen, and then C2H5. Of importance to note is that you try to retain these carbons 1, 2, 3. Whether it is an ester or it's a ketone, the propionyl or propyl group is very, very important for activity. So this chain is retained as a 3-carbon atom. Hope you're together up to there. I've explained keto, I've explained bemidone. Any compound that has a meta hydroxyl group on the phenyl ring, it will be called bemidone. When now you change the group at position number 4, one of the other groups, to a ketone rather than an ester, then you call it keto. Then you can see the other compound is being called alpha protein. When we talk about the alpha protein, these are compounds where now we introduce a small alkyl group there, like a methyl group. So when you introduce a small alkyl group, like a methyl group, at position number 3, we also do another change. we change such that the ketone, the ester which we have here, is reversed. That ester is not the way it is here. It is reversed so that you start with the oxygen. They have not done here the correct thing, so kindly correct that. So when we talk about the proteins, you see this name has changed and we are calling it a protein. Any compound that we are calling a protein is a compound that will have a methyl group. You can see like this one has a methyl group at position number 3. And then also this changes. It is not like that. It's supposed to be starting with an oxygen and then it comes C double bond O C2H5. So kindly correct that as you look at the notes. So this is what we call a reverse ester. So that is the proper ester. When you start with a carbonyl group, if you reverse the oxygen and the carbonyl group, you start with the oxygen, you call that a reverse ester. I hope you note, when it becomes a reverse ester, it implies we have no quaternary carbon, because what is joining the carbon directly now is an oxygen. So in the proteins will not have a quaternary carbon because you have a reverse ester, whereby the group that is joining the group, the carbon that's supposed to be a quaternary carbon, is joining with an oxygen and then a carbonyl group. And then you can see there is alpha. So there can be alpha and beta. This alpha and beta is because, as we said earlier, how is this methyl group? This methyl group at this position, how is it placed? And that again, we look at it. And in aridine, this is just like the other compounds we have mentioned. You can see it's a phenyl ethyl. Can you see it's an ethyl phenyl amine? So this, the only difference of this and the phenyl ethyl is just that group. And you remember that group is being put at that position. Everything else is the same. So those are the 4 phenyl piperidines which have the general structure as we have discussed. And I hope we are all together. Of course, when we now come to discuss them, I've mentioned them so that when we come to discuss, you have an understanding of the same. It's better to you understand as I explain, and then when now we come to the notes, it will be easier for us. So those are the 4 phenyl piperidines of interest. There could be others, but those are the ones that I've given you as our examples. Now, from there, remember, we said in the 4 phenyl piperidines, you have a subset of what we call the anhydropiperidines. I hope you can remember, we didn't mention the anhydropiperidines. Now, when you talk about the anhydropiperidines, there is a very slight difference. The fact that when you look at your phenyl group, I hope you can see what I am drawing. You find that in the anhydropiperidines, you find that the phenyl group, which is supposed to be joined directly to the piperidine ring in the 4 phenyl piperidine, is now joined, first of all, to a nitrogen. And after it's joined to a nitrogen, then the nitrogen is now what is joined to the 4 phenyl piperidine. So that is the main difference. When you talk about the anhydropiperidines, it is where, and I will repeat again, it is also, this here is 1, 2, 3, so you can have another substituent there. So it is where, and even that position, you can still have a substituent there, just as we discussed earlier. So in the anhydropiperidines, it is where the phenyl group and the piperidine ring are not joined directly to each other. No, or where the phenyl group is joined to the piperidine ring to give us a quaternary carbon. When we talk about anhydropiperidine, the phenyl ring and the piperidine ring are joined through a nitrogen. Let us be reminded that nitrogens and carbons, we call them isosteres, and of course, perhaps that is why it is possible. But the minute we join this drug this way, it gains maximum flexibility. it can be flexible, it can join, it can acquire different conformations, because you know that groups can rotate through, around sigma bonds. Groups can rotate using the sigma bonds, and therefore this molecule that we are calling the anilidopiperidine can undergo rotation, and it is flexible. And when it is flexible, it is able to fit the receptor very, very well. So now, when we talk about the anilidopiperidines, one of them being the basic one, again, the prototype being fentanyl, you find that fentanyl is very, very potent. Indeed, fentanyl is used in theater. It is used in theater as an adjunct to the general anesthetics, used in theater as an adjunct to the general anesthetic for that patient to have pain relief. So we have that these ones now very, very reactive, very high potency, and indeed these drugs are used as adjuncts to the general anesthetics in theater. And fentanyl, as I have said, is our prototype. The only difference, I've said again, is that these two rings are joined through a nitrogen. And you can see now this nitrogen has two substituents. It's still lacking in one. So the one it is lacking in, we can give it R1. We have also said this carbon here is lacking in one substituent, so we can give that R2. This here can have a different substituent. We can give that R4. This group here, just like in the proteins, it can also have a group there. We can give that R5. So you can see those are the substituents that we expect when we talk about the anilidopiperidines. The nitrogen can be substituted. The piperidine ring can carry 3 substituents for us, for the atoms to be completely satisfied. So fentanyl, as we look at this structure here, is our prototype. So again, the same R1 is what we are calling our R4 there. So carry the whole of this. It's an ethyl phenyl ring, and you bring it there. So that will be like phenazoxime, or it will be like phenethyl morphine. I hope you're there together. Then for the group, the other group now we have is this group here. And you can see in the anilidopiperidine fentanyl being our example, this group here is a hydrogen, and that is our prototype. Then you can see the group now that is joined now to the nitrogen, joined to the other group now. This is the whole group now here. The group now that is joined to this position, you can see we are starting here. So you have the group coming, joined to the nitrogen, and then the nitrogen is joined to a phenyl ring, and then finally joined. You can see the nitrogen, our nitrogen also, this R1, you can see our R1 there is a ketone. So we will see, we can't change this R here, and we can't change the group that is found, that is joined to the nitrogen. So let me first of all show you an example like the fentanyl, so that you can understand what you're talking about. So you can see this is our piperidine ring there. That is our piperidine ring, joined through a nitrogen, and then joined to the phenyl ring. So that's our phenyl ring, that's our piperidine ring. I hope everybody appreciates that the piperidine ring and the phenyl ring are joined through a nitrogen. They are not joined directly. That's what we are saying. Then now when you look at the nitrogen, just like the terminal nitrogen in any of the other drugs is joined to this big group, the phenethyl group. Then the nitrogen also, because of the fact that it has 2 substituents, it can carry a ketone. And when it carries a ketone, of course, the compound, as we had mentioned earlier, remember ketones, all these are amide. Amides are stabilized by resonance, so that compound is very stable. When you look at fentanyl, as we have already said, you look at fentanyl, as we have already discussed, then the substituent, so you can, if you look at this here, this is a carbon here. That carbon, you can see we have given it that substituent there, we have given it that substituent there, We have given that substituent there. So it doesn't have one substituent, and that substituent is the one we are saying for fentanyl. It is a hydrogen. So I hope you understand the structure. So for fentanyl is hydrogen, but for others it changes. So we'll go back. I hope you have understood how they sometimes when I explain it here, you might not understand how they are arranged, but now I hope you have understood how they are arranged. So now when we go to fentanyl, again you see the same group. This is joined to position number 1. Just like you have the methyl group at position number 1 of meperidine, in fentanyl, the same group as found in fentanyl. R2, which was a hydrogen in as you can remember, it was a hydrogen in fentanyl. You can see in fentanyl, it is an ester. That is an ester in fentanyl. The same group, it is anhydropiperidine. So you can see that group, all those groups are the same. Because remember, those are standard. These compounds are joined through a nitrogen and they have the ketone. So that is standard. The only group that can change is what is joined to the position 4 of the piperidine ring. So you can see in fentanyl, it is an ester. Again, giving that compound less stability because esters are quite easily hydrolyzed, and therefore that compound does not have a lot of stability. Sufentanil, and even as you can see, sufentanil, it means there is an S somewhere. The same kind of group. We have talked about that group there. We have talked about when we were discussing the non-steroidal anti-inflammatories, the thiophene, are isosteric. So all we have changed is isosteric replacement of the phenyl group with a thiophene group. And with the retention of activity, the other portion is the same. Now, the major difference is that in sufentanil, the ester, which is found in fentanyl, where you have a hydrogen, in fentanyl is replaced with an ether. Ethers have much, much more stability. So that compound is more stable than fentanyl. Then the other group is the same, as you can see. I forgot to tell you, fentanyl, kindly note, the piperidine ring at position number 3 also has a methyl group. Then we go to our fentanyl. Again, it's just changing the group. It's only the heterocyclic ring that is changing. Otherwise, the principle of the group is the same, and then it's joined here, and it's joined again to position 1 to the nitrogen. Remember, this is a group that is joined to nitrogen. Again, repeat, you have an ester there is joining through that. You can see that's the one which has CH2 joining through that. And the other group is the same because of these compounds, as we have said, are anhydropiperidine, and then it has a hydrogen. So those now are the anhydropiperidines. We have an example of fentanyl, sufentanil, lofentanil, and fentanyl. Those 4 are the anhydropiperidines, and there's just a bit of structural difference, just the way we talked about the structural differences in morphine and analogs, so that you can change the groups. But most of them, we have still good analgesic activity. The only thing that we are making in these compounds is that we can change the stability. When we put an ester, the ester is less stable than either a ketone or an ether. That is the only difference. Now from there, we move on to some other compounds, which we call pyramide and diphenoxylate. When you look at these compounds, they still share the same structure, they have similar structure with the other 4 phenyl piperidines. The only difference with loperamide and diphenoxylate is that now the groups are made very bulky. Very, very bulky. When they are made very, very bulky, these compounds have very, very high lipid solubility. These compounds, when you take them orally, because of the very, very high lipid solubility, they are retained within the GIT. because of the high lipid solubility, there is what we call depotization. With depotization, it implies these molecules are retained in the lipid layer. They are so lipid soluble, they cannot get out. They are trapped, they are sequestered, they are trapped there. And therefore, their ability they have is just to bind the receptors within the GIT. And when they bind the receptors within the GIT without getting absorbed, one of the side effects or one of the effects of the narcotic or opioids is causing constipation. That is a side effect of the opioids. So when you give, of course, constipation comes when the opioids bind the opioid receptors within the GIT. So when you give molecules that are structurally modified such that they are retained in the GIT, they will go for the opioid receptors within the GIT. And the only thing they can cause is constipation. So because they are causing constipation, it means if you give those compounds to somebody who has diarrhea, so you will stop their diarrhea. And that is how these two drugs, diphenoxylate, loperamide, although they are opioids, they only act within the GIT to bind the local or the GIT receptors. Just 1 minute, just one little minute, tafadhali. Just one little minute. I'm sorry about time. I engage people to prepare something and they're just conning me. Kenya is full of con men. Anyway, so we were looking at these two drugs, diphenoxylate, loperamide, and we are saying if you look at this group, I hope you can appreciate it's a very large group. And then you can see also there's another phenyl group added there. And therefore, these groups, because of the fact that they are very huge, they introduce very high lipid solubility. And these compounds are actually retained within the GIT. They are not absorbed, they are retained within the GIT. And once they are retained with the GIT, they only act as antidiarrheal agents. So if you look at diphenoxylate, again, that is our position one. I want you to appreciate the group that is all it does, it increases the lipid solubility extensively. Look at position number one. Again, they have introduced another big group, a phenyl group, again, further increasing the lipid solubility. This compound is retained within the GIT. The same case applies to the loperamide. At position, if you look at position again, number one, you can see the huge groups that are put there. Again, the issue here is that they increase the lipid solubility very highly. You can see the group that is put there, a chlorophenyl group, and halogens further increase lipid solubility. So that group extensively increases lipid solubility. That group extensively increases lipid solubility. These compounds are able to bind the opioid receptor, but since they are binding the opioid receptor mainly in the GIT, they are not being absorbed because of their very high lipid solubility. Of course, a bit can be absorbed and it will bring some side effects, but most of the drug is being retained within the GIT, and therefore the drugs act as antidiarrheal agents. So I hope that indeed actually almost finishes everything. I've basically explained everything that we are going to look at. So quickly, structure-activity relationship of the 4-phenylpiperidine. The representative 4-phenylpiperidine is meperidine or pethidine, which was first prepared as an antispasmodic. In addition to antispasmodic activity, it was found to be an analgesic, but with lower potency compared to the morphine. So the 4-phenylpiperidines were the first compounds which were found to have lower potency than morphine. Note that the compound follows the morphine rule, as we have discussed. This is meperidine, 4-phenylpiperidine. Here is our, as we have discussed, there is our in place of other groups that were there, we have put an ester that still brings us activity. Two-structure activity relationship. Meperidine is a prototype, has lower potency than morphine because it has good enough. We are not saying it has higher lipid solubility than morphine, but we are saying it has good enough, it has high lipid water partition coefficient, it has a short duration of activity due to the metabolism of the ester. It is an ester, and whenever you have an ester, you will have fast pass metabolism, and therefore it will have a short duration of activity. It has moderate bioavailability on oral administration due to fast pass metabolism. So it does not, because already it is metabolized even before absorption, it will have a low bioavailability. It has, and therefore, it will have higher parental than oral potency. And one of the most important things, as I had mentioned, it has rotation around the sigma bond and the benzene axial arrangement. Okay, it is connected on its own. Let us give it time again to connect. I don't know why, and my internet is very stable. I hope we are back. So all I'm saying is, of course, this is the meperidine structure. But for it to bind the receptor, we are saying the phenyl ring must acquire the axial. The axial is also the vertical. So that is how, in relationship to the other groups, it carries the vertical or axial orientation. And that is because it can rotate. These are sigma bond. It can rotate around the sigma bond, and once it rotates, the conformer, which is found to be most active, is when the benzene ring carries the axial conformation. If it carries the horizontal, then it will not have activity. So this is the active conformation of the meperidine. So that is why I wanted us to come there, so that we appreciate the next point, where we are saying has rotation around the sigma bond, and the benzene axial or vertical arrangement gives higher activity. The only disadvantage is that also the axial is the conformation which is more unstable. And therefore, the axial conformer, which binds the receptor optimally, is also the conformer, which is more unstable. It will be lower concentrations. So the axial conformer at the higher energy level than the horizontal conformer, which exists in higher concentration, but it's less active. So the horizontal conformer is at lower energy level, and therefore it will exist in higher concentrations. But remember, in the solution or within the receptor, you will have the axial and you will have the horizontal. Yes, the horizontal will be in higher concentrations, but it has poor binding to the receptor. The axial will be in low concentration because it's at a higher energy level, but it binds the receptor much more optimally. And that is why we are saying the axial conformer, although unstable, although at higher energy level, is the one which binds the receptor, and it is the one we require for activity. Therefore, it is even thought that meperidine may bind the receptor in a slightly different way from the rigid opiates, because you can see we are saying, although in the others we have rigidity, in morphine, in meperidine, in the 4-phenyl piperidines, we are advocating for flexibility, for that compound to be flexible, to rotate, to give us a specific conformer which has the best activity. And that is why it is thought that indeed the 4-phenyl piperidine, not only piperidine, meperidine, might bind the receptor differently. It has low receptor affinity and low antitussive activity. So that's why we are saying it has much, much lesser activity. Yes, it has good lipid water partition coefficient. It has high lipid water partition coefficient, but it has low receptor affinity when we compare it with morphine, and also it has low antitussive activity. So kindly remember those facts. Yes, even if a compound has very high lipid water partition coefficient or very high lipid solubility, if its ability to bind the receptor is low, if the concentration will be high, but it will not bind the receptor optimally, and that is why you will not get it giving you maximum activity. That is what can explain why meperidine has lower activity compared to morphine. The esters and reverse esters at the 4th position are active. You have seen the esters, as you have seen we have discussed, even fentanyl has an ester. And then I have said even reverse esters are also active. And you can see this is what I'm drawing here as an example of a reverse ester. A reverse ester is where you start with oxygen and then the carbonyl group. And a normal ester is like this one, the bemidone. You can see we have started the carbonyl group and we go to the oxygen. So kindly note, now, when we talk about the alpha proteins, the beta protein, they are reverse esters. You start with the oxygen, and when you start with the oxygen, means there will be an exception of the quaternary rule. The proteins will not obey the quaternary rule because one of the groups that will be attached to the quaternary carbon will be an oxygen. So kindly note the difference between a reverse ester and the normal ester. The normal ester starts with the carbonyl group, the reverse ester starts with the oxygen. But we are saying even compounds which have the reverse ester are also active. The simple ketones, like ketobemidone, are also active, and indeed they will be more stable. The propyl is the optimum chain length, excluding the ester oxygen. And if you look at all the groups, 1, 2, 3, whether it's a reverse ester, 1, 2, 3. So again, as we have discussed about that group, about the alkyl chain, or about the length of the chain being important because of the size of the molecule. So we require a 3-carbon chain, whether a reverse ester, whether a ketone, whether whatever it is, it requires to be a 3-carbon atom for maximum activity. So that is important. The phenyl ring and the 4 position, the pyridine ring, is again necessary for activity. That obeys the morphine rule, and therefore in all these compounds you will have a phenyl ring, and must, as we have already said, assume the axial position or the axial conformation if this drug is going to have maximum activity. Addition of a meta hydroxyl group, which we had mentioned, a 3' group, will enhance activity. Such analogs are called bemidones. Again, that I already discussed. When a reverse ester is combined again with a 3-methyl group, the analogs are known as proteins. Again, I've mentioned that. So you must have a reverse ester, you must have a combined with a 3-methyl group for you to call that compound a protein. And then we said you can have the alpha protein or you can have the beta protein. Just as we said of the benzomorphins, that you can have the alpha and you can have the beta. But of course, these ones, the alpha and beta, are because of different positions. So the positions which we are considering for the stereochemistry in the 2 groups are quite different. The methyl group may cause enantiomeric recognition by the opioid receptor. What does this mean? It is only meaning that there will be stereoselectivity. The methyl group, when you put it in position number 3, the resultant compound can either have the R or S configuration, and one of those configurations is the one of those enantiomers is the one which will have maximum activity. But again, remember, we are not only looking at one group, we are not only looking at one chiral center, we are looking at 2 chiral centers. So the stereochemistry, when we look at it finally, will be stereochemistry of 2 positions. As you see here, as we look at this, so this is position number 3 there. That is position 1, that is position 2, that is position number 3, that is position number 4, that is position number 5, that is position number 6, as we have discussed. So when you look at this, is a chiral center, whether you're looking at the reverse esters, because it's only the reverse esters that must be having, the reverse esters must have a 3-methyl group. So when you look at this group, and you can see it's a reverse ester, I hope you can see what we have discussed, that it's followed there. So this is a chiral center, and that is a chiral center. So we are saying in simplicity, the compound which we call the beta protein, position 3 has the R configuration, and position 4 has the R configuration. That's what I need you to remember. For one we call the alpha protein, position 3 has the R configuration, position 4 has the S configuration. So that is the only difference, that you can have the beta protein and the alpha protein. Again, the beta protein, just as we discussed earlier, the beta protein was found, the one which is beta was found to have much more activity than the compound which is alpha. And once it has more activity, it also means it will have higher liability. It has higher susceptibility to abuse. So you find that the ones which are clinically preferred are the alpha proteins, although they will have lower activity. So kindly, again, let us remember that, just as we discussed with the other compound, that of course the ones which are mainly preferred are the alpha proteins. I hope that is okay with us. That finishes, I think. That finishes. Oh, removal or replacement. So we are still on. We are continuing on with the phenylpiperidines. So we are also saying removal or replacement. We say the phenyl ring is a must. removal of the phenyl ring, either with an alkyl, aryl, or R-alkyl. Remember, R-alkyl is where you have an aryl group and an alkyl group. Always decreases affinity for the D site on the opioid receptor. Again, remember, in all these compounds require phenyl ring. So we are saying it is necessary for maximum activity. If you change it with any other group, you will decrease activity with the D site, and this is a D site. So you can see the phenyl ring is the one which interacts with the D site. The small hydroxyl group or methoxy group interact with another portion within the D site. So we are therefore saying we must have the phenyl ring, and that is why all these compounds do have that phenyl ring. Even if there is expansion or contraction of the phenyl ring into a 7 or 5-membered ring, gives compounds the analgesic activity, but less mu receptor affinity due to change in the relationship between the nitrogen and the change phenyl ring. So again, if you do contraction or expansion, you will change the interaction because you have changed also. Remember, there is a certain distance between the phenyl ring and the quaternary carbon and the terminal nitrogen. There is a fixed size between the phenyl ring and the terminal nitrogen. Phenyl ring is binding receptor. So if you change this ring, you contract it, you make it bigger. That means also you will change the position of the terminal nitrogen. It will not, the compound will not be able to interact with site D and site B simultaneously. So kindly note that when you change the phenyl ring, when you change the size of this molecule, it means it cannot be able to interact with the two sites simultaneously, and both sites are very important for analgesic activity. It might interact with that site, not interact with the other one, and therefore there will be a decrease in activity. So I hope you do understand that. So separation of the phenyl and the ester group decreases potency. This modification results in a change in the distance between the nitrogen and the phenyl ring, which is a critical feature for binding. It decreases the ability to bind the site D and C simultaneously. So you cannot by any chance, you cannot change the distance. You cannot change the distance between this phenyl ring. In fact, we should not even say with the ester. We should even just say we cannot change the distance between this phenyl ring, even with the terminal nitrogen. You cannot change that distance. If you change that distance, it means this compound will not be able to interact with the receptor effectively. And when that happens, then it means the compound will not have the maximum activity. I hope we are there. Us, and we are still on this phenylpiperidine. Insertion of a meta-hydroxyl group increases potency. Why? Because when you insert a meta-hydroxyl group, that hydroxyl group has its own area of interaction. You will increase the interaction of that compound with the D site, giving you much higher activity. Bemidone has a higher affinity for site D than meperidine, probably due to hydrogen bonding to adjacent site, which we have already seen. The bemidone are the ones which have the hydroxyl group on the 3' position. Conversion of the ester to a ketone increases potency and duration of action by increasing metabolic stability, as esters are hydrolyzed where ketones are not. So again, I'm just qualifying all the points I've told you. So if you have a bemidone, it is an ester readily hydrolyzed. If you have a ketobemidone, yes, that group is the same, but by virtue of the fact that this is a ketone not readily hydrolyzed, in fact, ketones are not hydrolyzed, this will be very easily hydrolyzed. Once it is hydrolyzed, you have broken one of the rules. This group should be a propyl chain for maximum interaction. If you hydrolyze it, you get a carboxylic group. Carboxylic groups for sure, two polar, they cannot even get to the site of action. So again, that is what we are talking about, that is the SAR, and we should be able to explain the SAR. We should be able to explain the SAR of these compounds, so that we just don't say you change this and this happens. You should be able to say, yes, when I change from an ester to a ketone, I expect more potency, I expect more activity, because the compound is more stable. When the compound is more stable, it means you can achieve higher concentrations. If you have higher concentrations, you have more molecules bombarding the receptor. And if you have more molecules bombarding or binding the receptor, you expect higher activity. So that is all we are talking about. So we are still reverse of the ester. Molecular modification stabilizes the resultant molecule when we do the reverse. For the reverse esters, the meperidine reverse ester, which we can say is N-methyl phenyl 4-propionoxy piperidine, has a longer duration of action. We are only saying it was found when this ester was reversed. When that ester was reversed, such that you don't start with the carbonyl group, you start with the oxygen. This is a finding which was found. Reversal of the ester stabilizes the resultant molecule. So this molecule was found to be a little bit more stable in terms of metabolic stability. So that was found when the receptor was reversed. Hello. Hello. I'm in class. Let me finish. So we are therefore saying when we reverse the ester, the methyl phenyl 4-propionoxy has a little bit more stability than the compound which has the other type of ester. And we are saying MPPP, which is the same one we have said there, has increased resistance to ester hydrolysis. Reversal of the ester group converts a stable group into a living group in vivo that produces another compound. All we are saying, yes, it is more stable. But unfortunately, when you take it and you have reversed the ester, when you take it in vivo, yes, there is more stability to hydrolysis, but it becomes what we call a better living group. It can live more easily. And when it lives more easily, that group lives. It becomes a better living group, the whole group. When that whole group leaves, what happens? You will just be left with that group here and the piperidine. Also, when that group leaves, it means that carbon will be dissatisfied. So there is a rearrangement of the bonds. So you can see the phenyl group remains the same, but the piperidine ring becomes a dihydro pyridine ring. So I hope you notice that difference. So we are saying, yes, the reverse ester is more stable to hydrolysis. But unfortunately, you see, these are findings which are found when the compound is investigated. It is more stable to hydrolysis, but unfortunately, it becomes a stronger living group. It can live easily. And once it lives easily, we are saying it's not easily hydrolyzed. The hydrolysis does not happen. So it is more stable to hydrolysis. It sticks. In terms of hydrolysis, it is not hydrolyzed, but unfortunately, it's a stronger living group, so all of it can live. And once it lives, then you have creation of this compound here, and that is a compound. This compound is just slightly different. You see, the other one was MPPP. This one now, if you look at this one, is no longer piperidine. Once it acquires one double bond, it means if it was, when we look at pyridine. Now it is, when it acquires one double bond, we now name it as a derivative of pyridine, no longer piperidine. So if you look at it, that compound, it has acquired that double bond there. So now we call it a derivative of pyridine, whereby if you look at it, that hydrogen there, that these bonds there have been saturated. So that bond there, so there's a hydrogen that has been added there. There's another hydrogen, that is 2 hydrogens. There's another hydrogen added there. There's another hydrogen added there. So we have 4 hydrogens. So we can call it tetrahydropyridine. Tetrahydropyridine, because it is pyridine saturated at that position and saturated at that position. I hope you are there together. So we are therefore saying the MPPP is converted to MPTP, and it is 1-methyl 4-phenyl 1,2,3,6 tetrahydropyridine. I hope you get it correctly. I hope you understand it just simple chemistry. It was piperidine before, and you can see the name is N-methyl, N-methyl, phenyl, phenyl, N-methyl, N-methyl, phenyl, N-methyl. The N-methyl means the methyl is joined to the methyl is joined to the nitrogen, and then phenyl, that phenyl, and then the 4-propionoxy, which is propionoxy because now we are starting with the oxygen. 4-propionoxy piperidine. You can see it's a piperidine derivative, and that we understand. But now the piperidine ring does not exist. In this group being removed completely, because as we have said, it's a good living group, the piperidine now has changed into a pyridine ring, but a pyridine ring that is saturated. If you consider position 1, position 2, position 3, position 4, position 5, position 6. So it is a pyridine that is saturated at certain positions. Otherwise, we should have double bonds. And that is why we are calling it 1, 2, 3, 6 tetrahydropyridine. And now this compound, when it is formed in the body, it is metabolized by the monoamine oxidase B to give us a highly toxic product. Highly toxic product, which now we call 1-methyl-4-phenyl pyridinium. Because if you look at it now, it is the whole pyridine, but it has a positive charge there. So now on metabolism, on oxidation, it gives us this compound called 1-methyl-4-phenyl pyridinium, and this is thought to be the result or the reason why some of these compounds, like when you have the reverse esters, like the proteins, it is thought to be the one which is responsible for their neurotoxicity. Whenever you see a compound here having a positive, that is a dangerous compound. We call it a reactive metabolite. It is an electrophile. It's a reactive metabolite. It can react within a site within the body, which has a negative charge and bind to it. And that is why these compounds are said to have toxicity. The reverse esters can have toxicity, which comes about because of generation of the phenyl pyridinium. And that generation is because you start with the reverse ester, loss of the propionoxy group to give us the tetrahydropyridine, and that then is further metabolized through monoamine oxidase B to give us the toxic metabolite. This is a neurotoxin, and that is what can these compounds. That's why these compounds can have toxicity. 1-methyl-4-phenyl pyridinium, MPP, is a positively charged organic molecule. It is a neurotoxin that acts by interfering with oxidative phosphorylation in mitochondria, leading to the depletion of ATP and eventual cell death. Or what we can actually, even if we leave all this, we can say it's a neurotoxin which can result in cell death that arises in the body as a toxic metabolite of the closely related compound. We have already mentioned that MPTP is converted in the brain into MPP plus by the enzyme monoamine oxidase B. We have looked at that, ultimately causing Parkinsonism by killing certain dopamine producing neurons in the substantia nigra. So all we are saying that is this is another side effect, and that's why some of these compounds, although they might have good activity, you will find that they are not being used in the body because of the fact that they have their toxicity. So the reverse ester, which are giving us the alpha and beta proteins, also can bring in unique toxicity. They can act as neurotoxins, as we have discussed, because of the conversion, first the tetrapyridine, and then to the pyridinium ion. And the pyridinium ion being charged, the charge makes it to be an electrophile, a reactive metabolite. When you are discussing about metabolism, you talked about that you can form electrophiles, which are reactive metabolites. And those electrophiles are the ones that undergo detoxification using glutathione. So if they deplete the glutathione as they are being produced, then there is a danger that if glutathione is depleted, then these compounds can now bind the neurons, the dopamine neurons, and bring about Parkinsonism. We are going to discuss Parkinsonism. I think it's also part of this unit. Parkinsonism, I think that will be our next topic. And you see, Parkinsonism is because of production of lower levels of dopamine. So we are saying these compounds will bind the dopamine neurons, lower the amount of dopamine that is produced, and therefore trigger Parkinsonism. Introduction of methyl to MPPP at position 3 results in the stereoisomers having different potencies. We have the beta protein has both high analgesic activity and toxicities, as we have already mentioned, than the alpha proteins. Absolute stereochemistry of the alpha and beta protein is beta protein has 3R, 4R, and alpha protein has 3R and 4S. Again, we had already discussed that. And we have said the beta protein, we have both high analgesic activity and also toxicity. So even if they were to be used, most probably we prefer the alpha proteins, just as we had said when we were looking at the benzomorphines. Nitrogen substituent. The SAR for the nitrogen substituent are similar to the epoxy morphinans. The epoxy morphinans, as we have discussed, are the morphine and the derivatives. The nitrogen substituent is a methyl in most cases, as we have seen, but of course not always. A phenethyl alkyl or its equivalent markedly increases analgesic activity, and we have seen that group in analidine, and also we have seen that group in actually the anilidopiperidines. Quite a number of them have that group. Fentanyl has that group, and the purpose of that group is to be able to interact with the A site and therefore increase the affinity or the analgesic activity of this compound. It is not possible to confer antagonist activity with a nitrogen substituent such as the allele as in morphine. So this was one of the major differences that was found, that in the 4-phenylpyridines, we could not at all. Remember, for the benzomorphines, we said when we put in a group that was introducing antagonist activity in the morphinans and the epoxymorphinans, the agonist ratio was higher than the antagonist ratio. Now, when it comes to the 4-phenylpyridines, it was found that even if you put a group like the cyclopropyl group, it did not introduce antagonist activity. And no wonder when we look at those compounds, those groups, like the allele group, we didn't see any compound with an allele group. We did not see any compound, the cyclopropyl group, or a cyclo or an alicyclic group at position number 1. That is being explained by this. It is not possible to confer antagonist activity with a nitrogen substituent such as an allele as in morphine. And therefore, those groups are not found in these compounds because they have no benefit, and antagonist activity is ending at the benzomorphines. The best antagonist activity is produced by the morphine analogs, because the morphine analogs, once you have the oxycodone, then you change the group at position number 17, as we had discussed earlier, you get pure antagonists. As we move on and we move to these other classes, even at butorphanol, which are morphinans, we realized that we will get compound with mixed agonist-antagonist activity. So pure antagonists are mainly from the morphine analogs. But first of all, you convert the molecule to oxymorphone by putting a ketone at position 6, saturating the double bond at position 7, 8, putting a beta hydroxyl group at position 14, and now changing the group at position 17, where now you either put an allele group or you put a cyclopropyl group. And when you do that, the resultant compound is an antagonist. But as you go down, as you continue changing the molecule, you reduce the antagonist activity, you come to partial, you come to mixed agonist, antagonist, until now you get to the for phenylpiperidines where we cannot develop antagonist activity. Antidiarrhea agents, which we have already mentioned, loperamide and diphenoxylate are opioid receptor agonists that act on the mu opioid receptors in the GIT. This is what we have mentioned. Loperamide and diphenoxylate lead to decreased gastrointestinal mobility and increased transit time. Loperamide and diphenoxylate increase the capacitance of the gut and delay the passage of fluid through the intestines. In simple terminology, they act as anti-diarrheal agents. They increase the motility. So if you're increasing the motility, that means they are making the gut to move, and therefore they will act. They also increase the transit time, so they will act as anti-diarrheal agent. Remember, constipation, the things are not moving. So when you get these drugs, they get into the GIT, they increase the motility, they increase the transit time, they are retained in the GIT. No wonder they will act as antidiarrheal agents. And that is their structure, as we've already discussed. Big, very huge groups that bring about very high lipid solubility. And because of that, then these compounds are retained in the GIT. The diphenoxylate is highly lipophilic. Diphenoxylate is in regular doses, has no CNS activity. So when you give it in normal doses, not unless if you want to abuse it. Any drug, when you abuse it and you give it in overdose, it will cause, of course, toxicity. But when you give it in the normal standard doses, it will not cause any CNS activity due to highly protein bound and sequestered within the lipid layer. So not only is it highly, does it have high lipid solubility, it's also highly protein bound, and it also has very high lipid solubility. It is sequestered within the lipid layer. Also, it's rapidly hydrolyzed to the carboxylic acid diphenoxine, which cannot penetrate the BBB. So this compound is also hydrolyzed to give us the diphenoxine. And once it does so, once it's hydrolyzed, the diphenoxine, which is a carboxylic derivative, does not penetrate the BBB. It does not penetrate the lipid. Even not only does not penetrate the BBB, so even it is absorbed, even if it's absorbed to get into the periphery, because of the carboxylic group, it will not penetrate into the brain. And I believe the hydrolysis at that point, because it's an ester, to give us the diphenoxine there, and the diphenoxine high water solubility. Now, so we are talking about in case you give it in very high doses, and we know we have also patient variation. Even if in a certain patient, a little bit of it is absorbed, we are saying it's undergoing very rapid hydrolysis, so it will not be able to penetrate the BBB, and therefore that it will not give us a toxicity. Even if it does minimal or insignificant toxicity. The loperamide, again, has very high lipid water partition coefficient and is free of all CNS effects, again, due to high protein binding, not free to penetrate the BBB, high lipophilicity, results in slow dissociation, and hence slow absorption and very poor bioavailability. And I have shown you why. It is because it has molecules that introduce very, very, very high lipid solubility. The compound also lacks water solubility, which prevents its abuse because it cannot be injected. So this compound, the loperamide, also lacks water solubility. If you inject it, it's not going to be absorbed, and therefore it is these two compounds, because of the high protein binding, the high lipid solubility, sequestering within the lipid membrane, and once they are sequestered, they are very little, if any, is absorbed, and hence you have, and even if they are absorbed, we are talking about very little will pass through the BBB, and therefore you cannot really abuse them. Even when you take them as anti-diarrheal agents, you will not really have the euphoria. That's what we are talking about. Because we abuse these compounds because of the euphoria. But because even if they absorb, they will be absorbed in negligible quantities. And then even when they absorb, they are not passing through the BBB. Remember, the BBB, the The euphoria is when these compounds pass through the BBB, they get into the brain, bind the opioid receptor, and bring about those effects. Since that is not happening, then they are not subject to abuse. It has high anti-diarrhea activity than diphenhexylate. So that is, you can see how change over structure can result in compounds that have very different clinical indications. Here we have diphenhexylate, loperamide, being used as antidiarrheal. We have the anilidopiperidine being used as 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 analgesics or as an analgesics in theater. You have these other drugs like pethidine being used as again as an analgesic in labor ward. What have we done? You have morphine being used, even being completely controlled because it's a drug of abuse. You have methadone being used when you go to Madara, you see that being used on those who are taking the morphines so that you can control their withdrawal symptoms. What are we saying? That you only need to structure and modify a molecule. And once you structure and modify a molecule appropriately, the molecule can give you the kind of activity that you desire. So the next is the anilidopiperidines. When it's about to finish, again, we have already discussed, we have said there is that group joined to the nitrogen. There is that group that must be there in all the molecules. The only group that changes is this group here, which we said that can be there. And of course, we also said you can, in some of them, you can have a group at that position. And I think I have drawn the several compounds. So you have the piperidine, the aniline, and of course, that is our anilidopiperidine. You can see that nitrogen, that's the piperidine, and that is our phenyl group joined through the nitrogen, and then you have our ketone, and that is definitely fixed, and that is the anilidopiperidine. Again, that's the numbering. You can see some of the compounds that I've drawn for you here. That is our fentanyl. That is a group which is very important. You can see that group retained there, that group retained there. So the group that is changing is this one here. You can see in lamifentanyl, it is also an ester, readily hydrolyzed, the compound having a short duration of activity. You can see in fentanyl, it's a hydrogen giving that compound stability. Then, of course, the group at the nitrogen can change. You can see that group there, you can see that group there. So those groups are the ones which are changing to give us the different activities. That is fentanyl again. Fentanyl, we have looked at it. Fentanyl, as we did mention, fentanyl has even a methyl group at that position, making that a chiral center, and that has having a slight influence on the activity of the different configurations. And this group, you see, I want us to understand that this group is retained as a constant. The group that is attached to the nitrogen is retained as a constant in all these compounds. It is what we said must be a propionyl group. It is retained as a constant. Now the group that changes is the group that is attached on the piperidine ring. You can't see there it is an ester. There it's a kit. There it is a hydrogen. You can see here also, this is an ether. That is also an ether. So kindly note, it is a group that is joined on the position 4 of the piperidine ring that changes. The group that is joined on the nitrogen remains a constant for all the compounds. And once you understand that, of course, the group also joined to the nitrogen can change. And that is why here you have the same group as found in fentanyl. Here we talked about sulfentanyl. It has that isoster of benzene. Here, again, there is a tetrazole moiety, only changing that group to see whether you still get the appropriate interaction. Remembering, of course, that as we have discussed, and as you discussed during drug development, discovery, and development, sometimes they try as many molecules as possible. Some of these the molecules are not just discovered easily. They are discovered after a lot of tests, whereby you keep changing the group, and you check again in the lab what is the influence on that group on the activity. Of course, there are some points you will have known. You will have known whether increasing lipid solubility will assist in the activity, whether increasing the electronic activity will increase on the activity. So you don't do it blindly, but you keep changing some of those groups, and then you test the molecule, and it's after the clinical, or after not the clinical, it's after the testing of the pharmacological activity, that now you can be able to tell that what the effect of that group is. And I believe when you are doing, there was that QSAR equation. You studied that equation, and you studied how you can change the different parameters of that equation to get differences in the ultimate activity that you get. We have already discussed at length about the anilidopiperidines, moving the phenyl ring from the direct attachment to the piperidine ring by one atom, which was the nitrogen, on the side chain, allows the phenyl ring to assume the more favorable axial conformation. So the minute you attach the phenyl ring with the piperidine ring through a nitrogen, you allow for movement around the sigma bond. You allow for flexibility. And once that molecule is flexible and it was able to attain the axial conformer, and the axial conformer was the one which was found to have maximum activity. The phenyl ring of the anilidopiperidine again also binds to the D site, just like the others of the receptor, similar to the ring A ring of morphine. So we are saying they will do the same. The binding is similar. There is no difference. The 3-hydroxyl group is not essential in the anilidopiperidines to bind the D site, unlike in the morphinans. And indeed, when we look at these drugs, kindly look at them, the structures. None has a hydroxyl group on the phenyl ring. So unlike all the others, the morphine and analogs, the morphinans, the benzomorphans, in this particular class of drugs, it was found you do not require the 3-hydroxyl group. Even for anilidopiperidines, again, remember we have said there is flexibility. So that ring is changing, and therefore the hydroxyl group might not be positioned at the area where it is supposed to interact, because of the fact that there is flexibility, and therefore the 3-hydroxyl group was found it was not essential. The anilidopiperidines are very potent synthetic analgesics used as an anesthetic. So they are used in the theater. They are used as theater, both as for pain. They are used in theater both as anesthetics, because they are very, very potent. And we have said the potency is only because of one thing: the flexibility of that molecule, such that when you get the axial conformation binds the opioid receptor optimally. Second to that, if you look at most of them, like if you look at fentanyl, you look at most of them also at position number 1 on the nitrogen. They also put a very large group, and that large group is able to interact. Most of those groups are alkyl groups, able to interact with the A site, and hence again including increasing the activity. Fentanyl is markedly more potent than morphine. Very, very potent, and no wonder it can be used as an anesthetic. Fentanyl has high mu receptor affinity due to binding to the A. Remember, the others were not binding the A. Why is it binding the A? Because it has the phenethyl group. It binds to B, it binds to C, it binds to D. So it binds to all the sites of the opioid receptor. Fentanyl also has a high lipid water partition coefficient or high lipid solubility, and can be absorbed through the skin and oral mucosa. The N, the nitrogen at carbon 4 in the alkyl group through the NCO bond increases the mu receptor affinity by correctly orienting the phenyl group. We are always saying when you put the nitrogen, that nitrogen in simplicity is just what we had said. When you put the nitrogen, it allows for flexibility of that molecule to give us the molecule or the conformer which maximally binds the receptor. Esters on nitrogen and carbon 4 on the nitrogen, in carbon 4 lead to rapid. I don't think I have any esters on carbon on nitrogen. My esters are on carbon 4. Esters on nitrogen and carbon 4 lead to rapid inactivation by plasma esterases in vivo, such as lamifentanil. I think when I look at lamifentanil, I always like looking at the lamifentanil is this one. Yes, this one has, this one has two. You see, now we have two nitrogen. So the nitrogen we are talking about, here I should put it correctly on the terminal nitrogen. Esters on this should be the terminal nitrogen, because again, we have another nitrogen. So esters on the terminal nitrogen and carbon 4 lead to rapid inactivation by plasma esterases in vivo, as in ramifentanil. And indeed, if you look at ramifentanil, it has two esters. It has this ester, ramifentanil. This is an ester there. So again, hydrolysis, ramifentanil, that is also an ester there at position number 4. So position number 4 and also the ester at the position is only number 4, and also on the nitrogen at position number 1. That makes that compound highly susceptible to ester hydrolysis. Again, esters are plenty in the body, and ester bonds are the activity. When you compare it to a compound like fentanyl, fentanyl has no ester, it has a ketone, highly stable. Also, fentanyl also has an ester, so even that one, but it is not as labile as lamifentanil, which has two esters. When you look at fentanyl, it has only one ester. So fentanyl has an ether, so that still gives it a bit of stability. Fentanyl also has an ether. So the ones which are the one which is most labile is lamifentanil. It should have the shorter duration of action, followed by fentanyl, but the others are quite stable. I hope we are together up to there. So that is to a repeat of what we have said. And I want to look at this one, will be our last slide. SAR of fentanyl on the piperidine ring. SAR of the 3-methylphentanil has higher analgesic activity and neurotoxicity compared to fentanyl. Again, remember, we did mention when you put a 3-methyl group, just as we have said, when you put a 3-methyl group in the alpha proteins, there is much higher activity. But the danger was that the resultant compound also had higher neurotoxicity, and therefore it was no benefit. And that is why the fentanyl is what is in the market, rather than the 3-methylphentanil, which supposedly has high activity. Larger groups, position 3, the pain relieving potency of the drug decreased. Again, when you put larger groups every time, remember sterichydrans. The size and shape of the group, rather than its chemical properties, play a crucial role in determining the fentanyl analogs effectiveness, the size and shape, because the size and shape will determine the sterichydrans. And I believe even when you looked at that equation we were talking about, sterichydrans was an important factor in determining pharmacological activity. So that group, when increased, we increase the sterichydrans, the compound is not able to access the receptor optimally, and therefore you have less activity. So we're saying cis-3-methyl and cis-3-ethylphentanil have a longer duration of action than their corresponding trans analogs. That's what was found, that the cis is the one which had higher activity than the trans. So those are findings. There is no reason perhaps you can be able, of course, it would mean the cis one is the one which has the better configuration of the better shape to interact with the receptor much more effectively. The stereochemistry influences the interaction with the body of pharmacodynamics rather than how it is absorbed and distributed. That's the pharmacokinetics. In other words, when you put a group like an alkyl group, it affects two things. When you add an alkyl group, it affects the lipid solubility. When it affects the lipid solubility, it will have an influence on the absorption because the compound has more lipid solubility. It will also have an effect on the metabolism. If it is in a position where it can be rapidly metabolized, it can shorten the activity of the compound. Or if it is if it just adds the lipid solubility, it can also increase the duration of action. But here we are saying it is not the lipid solubility of these molecules which is important. No, what is important is the steric hydrons. And I think we also mentioned that is where we are saying even if you increase lipid solubility, but the increase of the lipid solubility is through an introduction of a group that interferes with the shape of the ultimate molecule. Like when you put a methyl group for fentanyl or an ethyl group for fentanyl, or you put a big group at that position. When you put a big group at position number 3, it will interfere with the ability of this molecule to twist or to move around the sigma bond to give you the axial conformer. When you put a big group, remember, not only is it interfering with the accessibility of the receptor, it is also interfering with the ability of fentanyl to give us the axial conformer. Because you have this group that has brought in steric hydrons, it will not allow the phenyl group to acquire the axial conformation. So let us understand those two things. That not only is a large group interfering with the way this molecule access the receptor because of steric hindrance, it is also interfering with the way this molecule or hindering this molecule to get the axial conformer. And we have said the axial conformer is the one we require for maximum activity. For both the fentanyls, for both the 4-phenylpiperidines, we require the axial conformer. So what we are therefore saying, in these compounds, when you increase the lipid solubility, we must be careful not to interfere with the ability of this molecule to acquire the axial conformer or to access the receptor, because if we interfere with that, we may interfere with its activity. And that's all what we are saying, that the stereochemistry influences the interaction with the body or the pharmacodynamics rather than how it absorbs, rather than how it is absorbed and distributed. So here it is a pharmacodynamics of this molecule, because we must attain the axial conformer. We must also be able to get to the receptor, because when we get the axial conformer, that is the kind of the light shape for interacting with the receptors. Esters, again, this we had already mentioned, all the terminal nitrogen and also carbon fall into rapid inactivation that we had already mentioned. So we are only saying, even in fentanyl, you can put a 3-methyl group and it has more activity, it has neurotoxicity, so we forget it. If we introduce a bigger group, forget, the activity will reduce because of the failure of these compounds to give us the conformer, the axial conformer, which is responsible for maximum activity. And with that, this question ilinipatia, so sitaki ionekane hapo. So with that, we are done with the phenyl 4-phenylpiperidines. We are done with the anhydropiperidines, perhaps 1 or 2 compounds. Now we are just waiting for the last group, which will be the propanol, the phenylpropylamines. So we are only left with one group, the phenylpropylamines. Now where we will study the last compounds, like the methadones. So by the time we are done, we have finished all the narcotic analgesics. And when you go out there, you will be quite comfortable that you will almost know all of them. So with that, unless again there is any question, we can end there. As if there is a question. And then, as I say, the other, I'm having 2 classes for this unit, and the other class, they have been able to give me an extra class so that we finish early. When we finish early, she have been on mute. Or you can mute. Sini mumenisikia, I hope. Mumenisikia?
Yes, we have heard you, Doc.
Yeah? You could hear me?
Yes. We have.
Yes, because I found a message from Faith telling me I was on mute. Guys, that would almost kill my spirit. But you could hear me, yeah? I made a correction. All right.
Yes, we
So
have
thank,
heard you.
yes.
We have heard you.
You have, thank you, Getao. And kindly, if there is anybody who has any area they have not understood, I am your lecturer willing to go back and repeat it, hammer it in, so that when I give you a question, it might be just one question. But of course, there will be multiple choice questions. There could be a long answer question. There could be a short answer question. And of course, there is a cut. There's a cut we are going to do, and it will have questions in this area. So if you have any area where you are not clear, yes, I know that sometimes the chemistry is not easy, but we move along together. So if you have any question anywhere, you have not understood an area, do not be ashamed. All of us started there. Even me, I was a student who at times did not understand. What me I was is that I would have to ask because I believed I can understand. So if you don't understand, kindly disturb me. I am willing to be disturbed up to and before the exam. Of course, you cannot disturb me during the exam. Happen wewe na karatasi. So if there is anything you don't understand, kindly usiwe na woga ya kuongelesha mwalimu, kwa sababu mimi I'm not the young lecturers, I'm an elderly lecturer. I've been there when I was young. I have now come to be able to relate with my students. So feel free and do not feel that mwalimu atasema wewe ni mjinga. Hapana, kama sisi zote tulianza hapo, hatukujua, tukafundishwa, tukajua. Even me now as I stand, I don't know everything. There are areas like now what you guys are doing in pharmacology, pharmaceutical. I can't remember. I did those years almost 40 years ago. So kindly do not feel embarrassed. Do not feel shy. Ask me the questions. If you cannot ask me on the wall, call me. I believe you have my number or even just interact with me and let me be able to sort you out before the final exam, because I would want you to do my question and also pass that question. After all, you can see even I try to use as much energy as I can. So when you do my questions and pass them, I also am very excited. When you leave them out, it is very depressing knowing how many hours we have spent. So feel free to ask me questions before, of course, before 19th. I think we are finishing this semester on 19th. So before 19th, we will do our cut so that I'm left marking that cut. I should also have your assignments either this week. You can see the 5th years are bringing in theirs. You can also send in your assignments as early as possible. I see whether I can mark them as early as possible. So kindly let us do what is necessary. Thank you very much. Oh, today I can see you are 42. That is great. That is great. Kindly let us interact and let us not be ashamed of not understanding. And remember, even us, one day we were toddlers. We were where you are, we panicked over exams. Yeah, we used to get those panic attacks. So it is not anything different. It's not you getting those attacks and everything else or getting anxious is not anything new. Even us, we went through the same. Even me today, if I'm subjected, I'm told tomorrow Dr. come for an interview. Let me tell you, I will also be very anxious. So don't feel that you are so anxious, you don't know anything. No, be more willing to know. Have confidence and tell yourself, if I'm in 4th year, I can be able to understand. Yes, I can be able to do it. And once you do so, then you engage us as your lecturers, especially us who are willing to be engaged. Then now we explain to you better. You can ask me questions, and I can assure you at the end of the year, when you graduate in 5th year, you will one day perhaps give me a call. Like sometimes I'm given a call by my older students to tell me, thank you, Doctor. You worked with me. And now I am the superintendent pharmacist. See, doing where I am what company pharmacist, where I'm telling you the graduates of JQuat are doing miracles out there. So please engage us. Don't be embarrassed. It is always good to accept what you don't understand and be willing to ask. Kama mtu anakudharau kwa sababu hujui, wacha yeye akudharau. Lakini as long as you know what you are doing, you are inquisitive, you want to learn, you will learn. But if you keep quiet that you are scared, you will have that problem up to the exam. Now, when you come for the orals, Because remember, all of you, at the end of the year, you will do orals. You see, even if you didn't answer my question, the external examiner will ask you a question on this unit. Utanyamaza tu, utapewa marks tatu. And you know, when the marks from the oral exam, they're just good marks. You get from 1 to 10. So even if you had 40%, you got to 50 and you pass. So kindly, although you might not want to do my questions, I would plead with you to do my questions, but in the same breath, remember there will be an oral exam. So why would you come there and you cannot remember anything? So kindly engage me. I'm there for you. Thank you very much. Thank you. So class rep, Faith, I don't know when I can get the assignments. I'll be going for the others just now. When can I get your assignments? You can call me on phone. And also keep telling me which students are attending. Give me the attendance list every time we have the class. Thank you.